This is the first video on Chapter 42, the Fundamental Theorem of Calculus. And there's a little bit of a play on words here because all of my videos I have part 1, part 2, whatever. But the Fundamental Theorem of Calculus actually has two parts, a part 1 and a part 2. So video 1, part 1, will be on the Fundamental Theorem of Calculus, part 1. And the second video will be on the Fundamental Theorem of Calculus, part 2. Now, Fundamental Theorem of Calculus, part 1 is one that you're probably not going to appreciate quite as much as the Fundamental Theorem of Calculus, part 2. So, with part 1, we have a function f, the little f right here, the lowercase f, is continuous on the closed interval ab. We know that a continuous function on a closed interval is integrable. And so we define this function capital F of x. How? We make it the integral from a to x of f of t dt. And so this is how we're defining our function. Turns out capital F of x is continuous and it's differentiable. And now we take the derivative of capital F, which at first seems like a horrible, complicated thing to do, because we've defined f in terms of an integral and we're just now learning to integrate. So this is sort of a hard way to define a function, and now to even understand this, and now we want to take the derivative. Turns out the derivative is just f of x, where this is our function f. So we're going to do 3 examples. The first 2 are fairly straightforward, and the third one has a little bit of a twist to it. So the first one, we simply define f of x, the integral from 0 to x of this polynomial. Now there's nothing special about the a in this theorem. So there's nothing special about our starting point. We've defined capital F of x to be the integral from 0 to x of 4t squared minus t plus 7 dt. The derivative of capital F of x is 4x squared minus x plus 7. We simply substitute x in for this expression right here. Part B was made to sort of illustrate a point. We've defined g of x in terms of an exponential function. Exponential functions are part of Calculus 2, not Calculus 1. But here's what we need to know about this function, that it is continuous. So exponential functions are continuous. That's all we need to know. And so g of x is being defined the integral from 1 to x of e to the t squared plus t dt. And we want to find the derivative of g. That is simply e to the x squared plus x. And the only thing we need to know to do that is that this function, e to the x squared plus x, is a continuous function. Our third example is a little bit more complicated because we're not integrating from 0 to x or from some constant to x. We're integrating from a constant to a function of x. And we're defining capital F of x to be the integral from 0 to a function of sine of t dt. This is a composition of 2 functions. We have an inside function and an outside function. The inside function is the algebraic function, the square root of x cubed. And then the outside function is we're integrating from 0 to this function of sine t dt. When you're differentiating a composition of 2 functions, you use the chain rule. So the derivative is, we take the derivative of the outside function, we leave the inside function alone. Or another way to say that is we take the derivative of the outside function with respect to the inside function. This is our inside function. So we have sine of the inside function. Chain rule says the next step is to multiply by the derivative of the inside function, which is the algebraic function. So the square root of x cubed can be written as x to the 3 halves, so we can use the power rule. Just 3 halves multiplied by x to the 1/2 power. X to the 1/2 power, of course, can be written as the square root of x. So for this function here, we have to use the chain rule. because it's a composition of two functions.